So in this lecture I'm going to discuss systems of ODEs and how we can solve them numerically. If you recall the nonlinear pendulum, it was a second order nonlinear differential equation that we converted to a two-dimensional first order system. And the system that I have here includes a few more features than the one that we derived previously. This system includes a damping term, that is the minus dy sub 2 term, and also an external forcing term, that is the a sine t term. Okay, so this is a two-dimensional first order system that we can solve using a numerical method. There are some problems in this section that I may assign for homework that looks at this model. So more generally, if we have an nth order differential equation, we can always convert that to an n-dimensional first order system of equations. Okay, and so just as an example, let's look at some other nonlinear differential equation. Let's consider Blasius equation. Okay, so Blasius equation comes from fluid mechanics, and it's a third order nonlinear differential equation that goes by the following. It's f triple prime minus 1/2 f double prime equals 0. Okay. So it's nonlinear, and we want to convert this. What we want to try to do is convert this to a system, and it's going to be a three-dimensional system since Blasius equation is a third order differential equation. Okay, so to do the conversion, we set y1. We set y1 equal to f. We set y2 equal to f prime, and we set y3 equal to f double prime. And so by doing this, we have that y1 prime is f prime, which is y2. Basically, we want our right-hand side to be functions of y1, y2, and y3. Okay? And y2 prime is f double prime, which is y3. And so what is y3 prime? Well, y3 prime is f triple prime, and if we solve for f triple prime above, so f sub 3 prime is equal to 1/2 f double prime, and so what is f? F is y1, and f double prime is y3. So this is how we can convert third order differential equation to a three-dimensional first order system. Now, of course, we would need three initial conditions to have an initial value problem that we could try to solve. Okay, so now we're going to go and write down a general a two-dimensional first order system. So the general first order two-dimensional system. So consider y1 prime equal to f1, or a function of t y1 y2, and y2 prime equal to f2, which is a function of t y1 and y2. Okay, so this is a two-dimensional first order system. And now we'll use Euler's method, which Euler's method will have two formulas, one for y1 and one for y2. So Euler's method. And now we don't have to use Euler's method. We could use any one of the other two methods that we've learned, the explicit trapezoid method or the Runge-Kutta method. But there's a lot of bookkeeping involved when we're trying to solve systems of ODEs, and it's good enough to just use Euler's method for now, and then we'll try the other two methods at a later point. So for Euler's method has formulas. So we have now two indices. So we have w sub I plus 1, 1. And this is our approximation of y sub 1. And so w sub I plus 1, 1 equals w sub I 1 plus h times f1 evaluated at t sub I, w sub I 1, and w sub I 2. And w sub I plus 1, 2, which is our approximation of y sub 2, is w sub I 2 plus h times f2 evaluated at t sub I, w sub I 1, and w sub I 2. So you can see that there's a few things that need to keep straight here, and so let's look at an example now where we use Euler's method to solve a two-dimensional first-order system. So the example we're going to look at is y1 prime equal to y1 plus 3y2 and y2 prime equals 2y1 plus 2y2, and we have initial conditions y1 of 0 equals 5 and y2 of 0 equals 0. So what we're going to do is we're going to approximate we're going to do two steps of Euler's method. So we're going to approximate y1 of 0.5 and y2 of 0.5. Using two steps of Euler's method. So, to get things started, so for our solution, w sub 0, 1 is equal to 5, if you remember. Y1 of 0 was equal to 5, and w of 0, 2 equals 0. So these are our initial conditions. Of course, we have t sub 0 equal to 0, and now we can use Euler's method. So w1, 1 equals, it's w0, 1 plus h times f1 of T0, W01, W02. Okay. So, plugging things in, W01 is 5 plus H. In this case, if we want to use two steps and if we want to approximate Y1 and Y2 at 0.5, our step size is going to be 0.25. So H is 0.25 or 1/4. And so we have 1/4 times, now we evaluate F1, which was y1 plus 3y2. Okay, I guess I'll show, here are the equations for f1 and f2. f1 is y1 plus 3y2. f2 is 2y1 plus 2y2. And so now when we go to evaluate, so y1 is w01, which is 5, and then plus 3 times y2, of course y2 is w02 in this case, which is 0. Okay? So if we do this computation, we are adding 1 1/4 to 5, so we have 6.25. W sub 1, 2 is equal to W sub 0, 2 plus H times F2 evaluated at T0, W01, W02. And so this equals W02 was 0 plus H, which is 1/4. F2 evaluated at T0, W01, and W02 is, it's 2y1, or 2 times W01. So that is 2 times 5, and then plus 2 times y2, and y2 in this case is W02, which is 0. So if we do this computation, so we get 2.5 for W12. Okay, so now for the second step, so for the next step, we want to compute W21 and W22. And so W21 is given by this formula. It's W11 plus H times F1 evaluated at T1, W11, W12. So this equals W11, we just computed, was 6.25. And then plus our H, which is 1/4, times, we evaluate our function at T1, W11, W12, and so our function was y1 plus 3y2, so that turns into W11, which is 6.25, plus 3 times W1, W2, which was 2.5. So completing this computation, if you do the arithmetic, this turns out to be 9.6875. So this is our approximation of y1 at 0.5. And now we want to compute W22, and W22 is equal to W1, 2 plus H of F2 evaluated at T1, W11, W12. And so this equals, we computed W12 to be 2.5. Our H is 1/4. And our function F2 is 2y1 plus 2y2. And so that becomes 2 times W11, which is 6.25, and then plus 2 times, in this case y2 is W12, and W12 is 2.5. And so doing this arithmetic, we get that W22 is 6.875, and this is an approximation of y2 at 0.5. Okay. So certainly this is, there's bookkeeping involved, making sure that you have the indices correct. The second index refers to the variable, the y1 and y2. The first index refers to our step of Euler's method. Okay, and just as a note, this problem is actually, this is a linear first order system that can be solved analytically by finding eigenvalues and eigenvectors. So we could make a comparison, but for just most nonlinear systems of differential equations, there is no analytical solution. We have to resort to numerical methods. And of course, Euler's method is still the least efficient one of them. It would be better to use something like Runge-Kutta fourth order, even for systems. And as you could imagine, that bookkeeping would be really challenging, and Excel would come in really handy.